So, a little while ago, I asked you the following question. I have in my hand two magnets. The North Pole is shown in red, the South Pole is shown in silver. What would happen if I cut one of these magnets in half? Could I separate the North and South Poles? What do you think is going to happen? I asked my very glamorous lab assistant, Bradley, to help me find out. So, if we have succeeded in splitting the North and South Poles, then this little piece of North Pole I have should be able to pick up the South Pole, which, sure enough, it does, and it should then also repel the North Pole of this magnet. So this half of the original magnet is actually just acting basically like another little bar magnet. But why is that? To understand what's going on here, we need to talk about the origin of magnetism within matter. Something like a bar magnet behaves magnetically because it's surrounded by this invisible force field we call the magnetic field. Now, if we zoom in on the individual atoms that make up this bar magnet, what we find is that each one individually behaves rather like a little bar magnet themselves, with a North Pole and a South Pole. The reason that the atoms inside this bar magnet are so strongly magnetic is to do with the electronic structure of the electrons that surround this nucleus inside of the atom. Now, if we zoom in even further, we find that the majority of the contribution towards the magnetic field of the atom is coming from the electrons. The nucleus does make some contribution, but it is far smaller. Ultimately, what makes the electron magnetic is fundamentally a quantum mechanical property that we call the spin of the electron. Now, this is in some ways analogous to angular momentum, that is the kind of spinning momentum of the electron, but it's actually quite a bit more complicated than that, and really, this is just an analogy. So now we've established that the bar magnet is basically made of many, much tinier bar magnets. We can see why cutting the magnet in half does not separate the North and South Poles, but instead just leaves you with two smaller magnets, each with their own North and South Poles. The observation that there are no magnetic monopoles, that is, North Poles without South Poles, and vice versa, is first mathematically codified in the 1830s. Visually, what this law tells us about the magnetic field is that if you draw a surface, and as long as this surface is closed, the total number of magnetic field lines that enter the surface will always be the same as the total number of magnetic field lines that exit the surface. So, for example, here, the surface on the left, you see there are two entering at the top and two leaving at the bottom. The surface here on the right, you see that there are three entering in total, and then there are three exiting in total. Now, I should say that there are some more exotic theories in physics that predict that these monopoles should exist, but we've not yet seen any evidence of them. So as far as we know, they don't exist.